For this video, I'll demonstrate how to use Stata to conduct a one-way analysis of variance. And for this particular example, I'm going to use the growth and enhancement for Montana students data. And you can see by this message here, I already have that data set open. And so I'm going to go to the data browser and show you the variables that we'll use for this example. The first variable, or the grouping variable, will be class. And so we're going to compare AA, A, B, and C schools to or on ACT mean math scores. We want to determine if those students differ in terms of their ACT 12th grade math scores. Now, before we do this, we like to explore our data a little bit to get an idea of what it looks like and how that data meets the assumptions for the ANOVA. And the assumptions for the ANOVA analysis are that the variances should be equal, that the variables should be normally distributed, and we have independence of observations. So one way for us to do that is to go to graphs and construct box plots. And so we're going to do a box plot of ACT math scores for 12th grade by class. And so this is by class, AA, A, B, and C. And so we get a nice comparison here. Now remember, this is the median and not the mean. But nevertheless, it gives us a good overview of how these groups compare. And you can see that Class B schools are certainly smaller, or lower, I should say, than Class AA, A, or C. But the question is this difference large enough to be significant, or is this just due to sampling variability? And so we can save this, and I can save this as class box plots. So I can save this to my desktop or to any kind of a folder I have. Another graphic that we might want to take a look at is the histogram of this data. And so again, our dependent variable is ACT math at the 12th grade, and our grouping variable will be class. And so we can submit this. And so this gives us an overview or a histogram of that data. However, because of the sort of peaked nature of the data and the variability in this data, it's a little bit difficult to determine just visually if these data are significantly non-normal or not. So I'm going to save this graphic for future reference, and I'll save that to my desktop again. And so to determine if these groups have significantly non-normal distributions, one of the things we can do is go to statistics and classical hypotheses tests, or distributional plots and tests. And we can go to the Shapiro-Wilks test. And so this test, again, will determine if the data by group is significantly non-normal. And so again, we're going to use class as our grouping variable. And so our output, we can see that we get class AA, A, B, and C. And each result has a W value, which is the Shapiro-Wilks statistic, and a probability. And in this case, the probability is 0.009, which is much smaller than 0.05. So this means that this distribution is significantly non-normal. However, for class A, B, and C schools, the probability of non-normality is not significant. So these variables are not significantly skewed. Okay? So what we want to do now, or I should say significantly non-normal. So now the other assumption we want to test for is to determine if the variances between groups or classes of school, variances on ACT 12th grade math scores are similar or not significantly different. So we can go to statistics, and then we can go to robust equal variance test. And our variable again is ACT math, and the groups we want to look at are class. And we can go OK. And so we're going to look at this first result, WO, and this is 0.31. So this is clearly above 0.05. And what it indicates is that the variances that are derived, the variances that the standard deviations are derived from, are not significantly different. So even though we have partially violated one assumption, the assumption of non-normality in one of the groups, the class AA group, we've not violated the assumption of homogeneity of variances. So ANOVA is robust to the violation of one assumption, but not two. If we violated both assumptions, then we'd probably want to do some sort of a non-parametric procedure. But we're going to go ahead and run the ANOVA analysis. We're going to go ahead and do that now. So we go to linear models and ANOVA, MANOVA, and then one-way ANOVA. Now our response variable is, again, our dependent variable is ACT Math 12. And our factor variable is class. And then we might want to do a post hoc test, because if it turns out that there is a significant difference, if the ANOVA is significant, then we need to determine which groups differ significantly from one another. And so what the multiple comparison test or post hoc test does is that it allows us to do multiple comparisons between those class groups, but it holds the type 1 error rate to 0.05. And then we want to get the ANOVA summary table. So I'm going to go OK, and we get our output for the ANOVA. So these are our means. These are the standard deviations. And of course, these are the frequencies in each group. This is our ANOVA summary table. And our ANOVA summary table is just barely not significant. And then we see that we do have confirmation that our variances are equal using the Bartlett's test rather than the Levine's test that we just did. So we can see that this is just barely significant. So we can see that with the multiple comparisons test, that if I compare class A to class AA, the difference between these means is negative 1.20 ACT score points. So if I go up here, what this is saying is that this mean subtracted from this mean is minus 1.2. And that difference is not significant because this probability is above 0.05. Now, if I subtract or compare Class B to Class AA, so I'm subtracting this mean from this mean, 19.84 from 22.67, that difference is negative 2.83. And this is highly significant. So what we can say here is that Class B ACT 12th grade math scores are significantly lower than Class AA. And then if I compare Class C to Class AA, so I subtract 21.93 from 22.67. That difference is 0.74, very small. That is not significant. So that's how you read these tests. If I compare Class B to Class A, so I subtract 19.84 from 21.47, you can see that this difference is not significant, 0.414, as compared to our threshold of 0.05. And then comparing Class C to Class B, there's a 2-point difference in those means, and again, that is not significantly different. Another important result to interpret for the ANOVA analysis is the effect size. And for this particular analysis in Stata or approach, the effect size is not calculated for us, but we can very easily calculate it. So the effect size basically tells us how strong or the magnitude of our result. And so to get the effect size for this particular example, we divide the between groups variability. So the variability in Math 12 ACT scores divided by the total variability. And so I've done that here, and you can see that 301.94 divided by 7143.64 gives us 0.04. And so according to Cohen, this is really in between a small and a moderate effect. So it's not a very large effect in this case. So those differences, I would say, are not very meaningful. Another way to look at or interpret this effect size is we can say that 4% of the variance in ACT 12th grade math scores is due to school class group differences.